Across the vastness of space, orbiting stars both near and distant, lie a collection of planets that challenge our understanding of habitability and the uniqueness of life on Earth. Over the course of this investigation, we have journeyed through more than 20 confirmed exoplanets, each bearing characteristics that make them potential cradles for alien biology. When we take them together, the question isn't just whether life exists elsewhere, but how common it might be in our galaxy. K218b is an exoplanet orbiting the red dwarf star K218, located approximately 124 light-years from Earth in the constellation Leo. Discovered in 2015 by NASA's Kepler Space Telescope during its K2 mission, K218b quickly gained attention for being one of the first exoplanets in the habitable zone with detected water vapor in its atmosphere. With a radius about 2.6 times that of Earth and a mass nearly 8.6 times greater, it is classified as a sub-Neptune or mini-Neptune, placing it in a category of planets not found in our own solar system. K218b orbits its star once every 33 days and receives roughly the same amount of stellar radiation as Earth does from the Sun. Despite the similarity in insolation, the planet itself is quite different from Earth in structure and atmospheric conditions. Its large size and mass suggests that K218b is not a rocky, terrestrial planet, but instead has a thick hydrogen-rich envelope surrounding a possible water or rock core. This atmospheric composition and internal structure make it unlikely to have a solid surface in the way Earth does. Instead, the planet may have a deep, dense atmosphere with layers of gas above high-pressure oceans, or even supercritical fluids far below. In 2019, observations using the Hubble Space Telescope detected water vapor in the planet's atmosphere, making K218b the first known exoplanet in the habitable zone to show evidence of this vital molecule. The presence of water vapor, especially in a temperate zone, is a major milestone in exoplanet science. However, the detection alone does not confirm the existence of liquid water on the surface, or indeed any surface at all. The temperature and pressure conditions beneath the thick atmosphere are still poorly understood, but modeling suggests that depending on the depth of the atmosphere and the concentration of greenhouse gases, conditions could range from mildly temperate to extremely hostile. One of the central questions surrounding K218b is whether its environment could be compatible with life. Life as we know it requires stable conditions, access to liquid water, and a source of energy. The detection of water vapor and the planet's location in the habitable zone satisfy two of these criteria in a broad sense. But whether the third, stability, is present depends heavily on the atmospheric dynamics and potential energy gradients within the planet's deep atmosphere. In 2023, the James Webb Space Telescope JWST observed the atmosphere of K218b using its NIRSPEC instrument. These observations revealed not only more robust signs of water vapor, but also hints of other molecules such as methane CH and carbon dioxide CO. The simultaneous detection of methane and carbon dioxide is particularly intriguing because on Earth, their co-presence in a stable atmosphere is often associated with biological processes. These gases could in theory represent a possible biosignature if they exist in the right ratios and concentrations. However, they could also be produced through entirely abiotic mechanisms, especially given the hydrogen-rich composition of the atmosphere. More controversially, the JWST data included a potential detection of dimethyl sulfide DMS, a molecule on Earth that is primarily produced by marine phytoplankton. If confirmed, the presence of DMS in the atmosphere of K218b would represent a strong biosignature candidate, as it is difficult to produce abiotically in hydrogen-rich environments. However, this detection remains tentative and is the subject of ongoing analysis and scrutiny. False positives are a significant concern in exoplanet atmospheric studies, particularly when interpreting spectral signatures from such vast distances. The internal structure of K218b also complicates the case for life. Given its size, the planet likely lacks a solid surface and instead may have a deep ocean covered by a dense atmosphere, what some researchers term a Haitian world, short for hydrogen ocean. In such planets, life would need to exist either in a liquid ocean beneath the atmosphere or within the atmosphere itself, possibly floating in cloud layers where temperatures and pressures are more Earth-like. This hypothetical scenario, inspired by life in Earth's upper atmosphere, opens a new avenue for considering life not as something tied to solid ground, but as an airborne phenomenon existing within stable atmospheric layers. Still, the challenges for life in such an environment are immense. Hydrogen-rich atmospheres can be chemically reductive and may not support the same kinds of organic chemistry found on Earth. The pressure and temperature deep within the atmosphere or ocean could also be extreme, posing additional barriers to life. Moreover, ultraviolet radiation from the host star could break down key molecules, although this may be mitigated by cloud cover or by life existing beneath the upper layers. The star K218 is a red dwarf, and while it is not currently classified as particularly active, M dwarfs are known for their unpredictable flaring behavior, especially during their early years. High-energy flares could erode planetary atmospheres or sterilize surface environments if magnetic protection is weak or non-existent. However, K218b's thick atmosphere might offer some protection from such radiation, particularly if the planet has a magnetic field. Another concern is whether the atmospheric features observed represent stable, long-term conditions or transient phenomena. Planetary atmospheres are dynamic, and methane and water vapor can rise or fall in abundance due to changes in temperature, internal chemistry, or even atmospheric escape processes. Determining the chemical equilibrium and long-term evolution of K218b's atmosphere will be essential for understanding its true habitability. At this stage, K218b represents one of the most promising yet enigmatic candidates for hosting alien life. Its large size and thick atmosphere may make it inhospitable to Earth-like organisms, yet they also provide an insulating environment where water and potentially life-supporting chemistry could persist. The tantalizing detections of water vapor, methane, and possibly dimethyl sulfide hint at the potential for life. But these signatures alone are not proof. More detailed spectroscopic studies and future JWST observations may help confirm the presence or absence of true biosignatures. Advanced atmospheric modeling, combined with observations from telescopes like the Extremely Large Telescope ELT or proposed future space missions, will be necessary to clarify the planet's composition and chemistry. These tools may one day allow scientists to determine whether the signatures we see are biological in origin or the result of exotic but abiotic chemical processes in a unique planetary environment. In summary, K218b offers an extraordinary case in the search for extraterrestrial life, a planet in the habitable zone with a detectable atmosphere, known water vapor, and possible biosignature gases. Yet it remains fundamentally alien in structure and likely harbors conditions far removed from the familiar environments of Earth. Whether it supports life or not, K218b challenges our understanding of habitability and reminds us that life, if it exists elsewhere in the universe, may flourish under conditions we have only just begun to imagine. Kepler-62f is a confirmed exoplanet orbiting the star Kepler-62, located approximately 1,200 light-years from Earth in the constellation Lyra. Discovered in 2013 by NASA's Kepler Space Telescope using the transit method, Kepler-62f has been one of the most promising Earth-sized exoplanet candidates found to date, primarily due to its size and its position deep within the habitable zone of its star. It is the outermost of 5 known planets in the Kepler-62 system and orbits its host star every 267 Earth days. The host star, Kepler-62, is a K-type main sequence star with about 69% of the Sun's mass and around 21% of its luminosity. It is cooler and slightly older than our Sun, estimated to be around 7 billion years old. This type of star has a more extended and stable lifespan than the Sun, providing a long-term energy source that could allow life on surrounding planets to emerge and evolve over billions of years. Kepler-62f has a radius approximately 1.41 times that of Earth. While its exact mass is not known, models based on its size suggest that it likely has a rocky composition, possibly with a solid surface. If it is rocky, Its mass could fall somewhere between 2 and 3 Earth masses, with a surface gravity potentially up to 1.6 times that of Earth. This increased gravity would be strong enough to retain a thick atmosphere, essential for climate stability and the potential for life. Its orbital distance, about 0.718 AU from its star, means it receives roughly 41% of the solar flux that Earth receives from the Sun. While this places it on the colder end of the habitable zone, it is still well within the conservative boundaries where liquid water could exist, depending on atmospheric conditions. On a planet like Earth, this level of solar flux would produce a global average temperature below freezing, but even modest greenhouse warming could raise temperatures into the habitable range. Climate modeling of Kepler-62f has produced a wide variety of possible scenarios, ranging from frozen desert worlds to fully temperate ocean planets. One key factor is whether the planet has a dense atmosphere rich in greenhouse gases like carbon dioxide. Models suggest that an atmosphere composed of at least 5 bars of cold could warm the planet enough to allow for stable surface liquid water across broad regions. If the atmosphere is thinner or composed mostly of nitrogen and oxygen like Earth's, large areas of the planet might remain frozen, with habitable conditions limited to the equator or low-altitude basins. Another critical factor is cloud behavior. Planets with thick water clouds could reflect more sunlight and cool the surface, while thin, high-altitude clouds could trap heat and enhance warming. These effects are difficult to model accurately, particularly for planets we cannot yet observe directly. However, a combination of a moderately thick atmosphere and cloud feedbacks could allow Kepler-62f to maintain habitable surface conditions even with relatively low stellar energy input. Because the planet transits its star, we know its radius with precision, but its mass remains unmeasured due to the distance and faintness of the system. Despite this, Kepler-62f is widely assumed to be terrestrial rather than gaseous, based on statistical comparisons with other exoplanets of similar size. It is unlikely to be a mini Neptune, which typically have larger radii above 1.6 Earth radii and thick hydrogen-helium envelopes. As a potentially rocky planet in the habitable zone, Kepler-62f is one of the best candidates for the presence of surface water and, by extension, life. If the planet has retained water over geologic time, and if it formed with a similar proportion of volatiles as Earth, it could possess oceans, lakes, or rivers, particularly in warmer regions of the planet. A global ocean is another possibility, especially if the planet has a relatively uniform surface with no significant landmasses. Its distance from the star also means Kepler-62f is less likely to be tidally locked, which is a common concern for planets around smaller stars like M-dwarfs. Because Kepler-62 is a K-type star and the planet has a relatively wide orbit, it is probable that Kepler-62f experiences day and night cycles similar to Earth's, allowing for more even heat distribution and possibly a more Earth-like climate system. This rotational freedom may also enhance the development of a protective magnetic field, assuming the planet has a molten, convecting iron core. Kepler-62f's age, likely around 7 billion years, adds to its potential. If life were ever possible there, it would have had a significantly longer span of time to emerge and evolve than life has had on Earth. However, it's also possible that if the planet's environment became too cold or lost its atmosphere over time, life may never have gained a foothold or may have gone extinct. There are no observational constraints yet on Kepler-62f's atmosphere or surface conditions. Its extreme distance makes it inaccessible to current instruments for atmospheric characterization. However, it remains a prime target for future direct imaging missions and high-resolution spectroscopy with the next generation of space telescopes. These could, in time, search for biosignatures, such as oxygen, ozone, methane, or other gases that are typically produced and maintained by biological processes in Earth's atmosphere. Speculative though it is, life on Kepler-62f, if it exists, would have to adapt to a different spectrum of sunlight, longer years, and possibly colder climates. If the planet is an ocean world, life may exist exclusively underwater, shielded from ultraviolet radiation and temperature extremes. Alternatively, if the planet has continents and varied terrain, life could resemble early microbial forms or even complex ecosystems if environmental stability has persisted. In conclusion, Kepler-62f is one of the most promising exoplanets identified to date for potential habitability. It is almost certainly rocky, resides within the habitable zone of a long-lived and stable star, and has a radius and orbital period consistent with Earth-like conditions, given a suitable atmosphere. While no evidence of life has been detected and no atmospheric measurements have been made, it remains a compelling target in the ongoing search for worlds where life may have taken hold beyond our solar system. Whether it is a frozen wasteland, a water-covered planet, or a temperate Earth analog awaits the technological advances of the next generation of astronomical observation. Gliese 163c is a confirmed exoplanet orbiting the red dwarf star Gliese 163, located about 49 light-years from Earth in the constellation Dorado. Discovered in 2012 by the European Southern Observatory's HARP spectrograph, it is one of at least 3 planets in the system and stands out due to its location near the inner edge of the star's habitable zone, with a minimum mass of approximately 6.8 times that of Earth. Gliese 163c is classified as a super-Earth, likely possessing a rocky composition or a dense water-rich interior. The planet completes an orbit around its host star every 25.6 Earth days. This rapid orbit is made possible by the low luminosity of Gliese 163, a relatively cool and dim M dwarf with about 40% of the Sun's mass and less than 3% of its luminosity. Gliese 163c orbits at a distance of roughly 0.125 AU, much closer than Mercury is to the Sun, but due to the low energy output of red dwarfs, it still receives about 1.34 times the solar flux that Earth does. This places it just inside or on the inner edge of the star's conservative habitable zone. That position raises a critical question: is Gliese 163c too hot to support life? Whether the planet experiences a runaway greenhouse effect, like Venus, or maintains moderate, life-supporting conditions depends heavily on its atmosphere. If it has a dense, water-rich atmosphere with thick cloud cover, reflective aerosols could potentially cool the surface and stabilize the climate. On the other hand, if the atmosphere is rich in greenhouse gases and lacks cooling mechanisms, surface temperatures could rise to uninhabitable levels, evaporating any liquid water. Like many exoplanets orbiting close to red dwarfs, Gliese 163c is expected to be tidally locked, with one hemisphere perpetually facing the star and the other in permanent darkness. This configuration can lead to extreme temperature contrasts across the surface. However, if the planet has a sufficiently dense atmosphere, particularly one that includes greenhouse gases and water vapor, then heat could be efficiently distributed from the day side to the night side through atmospheric circulation. Climate models suggest that such planets could support habitable regions, especially in the terminator zone between day and night, or across broader areas if the heat redistribution is strong. Gliese 163's minimum mass indicates a planet with strong gravity, likely between 1.5 and 2 times Earth's surface gravity, depending on its actual radius. This gravity would help retain a thick atmosphere over geological timescales, a critical factor for habitability. Strong gravity also stabilizes surface pressures and supports long-term geological activity, such as volcanism, which could provide a steady release of gases into the atmosphere and maintain temperature stability. The planet's potential composition is not yet known with certainty. However, with a mass near 7 Earth masses, Gliese 163c could be a rocky super-Earth or a water world with a substantial layer of high-pressure ice and liquid water beneath a thick atmosphere. If it is rocky, it may resemble a hotter, denser version of Earth or Venus, with either a dry, greenhouse-stricken surface or a cloud-covered ocean planet. If it is a water world, it might lack a solid surface and instead feature a global ocean, possibly hundreds of kilometers deep, overlying a rocky mantle. Such planets could have subsurface conditions suitable for life, especially near hydrothermal vents at the seafloor, where geothermal energy could fuel microbial ecosystems. The presence of life on Gliese 163c would depend on the availability of water, energy, and essential elements. Water is likely, at least in vapor form, due to the planet's mass and potential to have formed with volatiles. Energy could come from stellar radiation or internal geothermal sources. The planet may also have experienced significant migration from farther out in the system, bringing ices and volatiles with it during formation. If life exists, it could take the form of extremophiles adapted to high surface temperatures, intense radiation, or deep subsurface oceans where it is shielded from external conditions. Gliese 163 itself is a relatively quiet red dwarf, with lower stellar activity than many of its peers. This is important because flares and strong ultraviolet and X-ray radiation from young or active red dwarfs can strip planetary atmospheres or sterilize the surface. The apparent low activity of Gliese 163 increases the chances that its planets could have retained atmospheres and avoided catastrophic radiation exposure over time. One of the greatest limitations in evaluating Gliese 163's habitability is the absence of transit data. Because the planet does not pass in front of its star from our point of view, we cannot observe starlight filtering through its atmosphere during transit to determine its composition. As a result, we have no direct information about its atmospheric thickness, surface temperature, albedo, or pressure. All inferences are drawn from indirect modeling based on its orbit, stellar radiation, and mass. Simulations of the climate and energy balance of Gliese 163c under various atmospheric compositions produce a wide range of possible outcomes. Some models suggest that, with the right atmospheric pressure and cloud behavior, the planet could maintain surface conditions suitable for liquid water, particularly in regions receiving moderate and consistent stellar energy. Others caution that the inner edge location and high insolation make it more likely to have undergone a runaway greenhouse process, in which all surface water evaporated and the atmosphere became dominated by dense carbon dioxide, creating uninhabitable surface conditions. From a biosignature perspective, Gliese 163c remains inaccessible to current instrumentation. The planet's orbit and lack of transit make it challenging to target for atmospheric spectroscopy with telescopes like the James Webb Space Telescope. Future missions capable of directly imaging exoplanets, such as LUV, OI, R, or HABEX, may one day be able to analyze its atmosphere for signs of gases like oxygen, ozone, methane, or combinations that indicate disequilibrium and possible biological processes. In conclusion, Gliese 163c is a strong candidate for potential habitability, sitting on the edge of possibility. Its mass, proximity to a stable red dwarf, and location near the habitable zone make it a compelling subject of study. It could be a hot, barren planet similar to Venus, or it could be a world with dense cloud cover and moderated temperatures, potentially hosting life. It may even have vast oceans beneath an atmosphere thick enough to support life below the surface, far from the harsh radiation of its star. At present, there is no direct evidence of life on Gliese 163c, but it remains a key object in the catalog of exoplanets with conditions that may support it. Whether alive or lifeless, it continues to expand the boundaries of what we consider possible in the search for life beyond Earth. Proxima Centauri b is a world that orbits the closest star to our Sun, and as we begin this quiet journey across the cosmos, let us gently drift into the velvet silence of space to learn about this intriguing exoplanet, one of our most promising candidates in the search for alien life. Imagine yourself floating in the vast ocean of the Milky Way. The stars above shimmer softly, as if blinking through the veil of time. And there, not too far from our own celestial neighborhood, just a little over 4 light years away, shines a faint red star known as Proxima Centauri. Barely visible to the naked eye from Earth, this red dwarf star sits in the southern constellation of Centaurus. It's the closest stellar neighbor to our solar system, quietly glowing with a cool, steady light. In 2016, astronomers using the European Southern Observatory's HARPS instrument in Chile made a remarkable discovery, a rocky planet orbiting this nearby star. That planet, Proxima Centauri b, lies within its star's habitable zone, the region around a star where conditions could be just right for liquid water to exist. And with water, of course, comes the tantalizing possibility of life. Proxima b, as it's often called, is at least 1.17 times the mass of Earth. It completes a full orbit around its host star every 11.2 Earth days, which means that a year there passes in less than 2 weeks here. Despite its close orbit, it receives roughly the same amount of stellar energy as Earth does from the Sun. That's because Proxima Centauri, though nearby, is a red dwarf, cooler and dimmer than our Sun. The thought of a planet so close, yet so alien, sparks the imagination. What would it be like to walk upon its surface? Would the sky be painted with the dull crimson hue of its parent star? Would strange winds blow across barren plains or perhaps whisper through ancient forests unlike any we've ever known? We don't yet know what Proxima b looks like, but its discovery was the result of years of patient, precise measurements. Astronomers detected a slight wobble in Proxima Centauri, tiny shifts in the star's motion caused by the gravitational tug of an orbiting planet. This method, known as the radial velocity technique, doesn't give us a direct image, but it allows us to infer a planet's presence, mass, and orbit with impressive accuracy. Since its discovery, Proxima b has become a focal point for astrobiology, planetary science, and even dreams of interstellar exploration. Being the nearest known potentially habitable exoplanet, it holds a special place in our collective imagination. Scientists and engineers have even proposed future missions to explore it, including the Breakthrough Starshot Initiative, a project aiming to send tiny lightweight spacecraft propelled by laser sails to Proxima Centauri within a few decades. If successful, these craft could capture the first close-up images of this mysterious world. But what truly makes Proxima b so fascinating is its potential for habitability. The planet sits in what we call the Goldilocks zone, not too hot, not too cold. Its rocky composition suggests a solid surface, perhaps with oceans or continents. Theoretically, if Proxima b has an atmosphere, and we still don't know for sure, it might help distribute heat and protect against solar radiation. However, life on Proxima b wouldn't be easy. Proxima Centauri is an active star, prone to frequent flares. These outbursts of radiation could strip away a planet's atmosphere over time, especially one so close to its star. But if Proxima b has a strong magnetic field, like Earth's, it might shield itself and maintain conditions suitable for life. There's another twist. Proxima b may be tidally locked. That means one side of the planet could always face its star in perpetual daylight, while the other remains in eternal darkness. If this is true, then perhaps life, if it exists, could find a home in the twilight zone, the temper band between the hot day side and the frozen night. It's a poetic idea, a world split between fire and ice, with a narrow ribbon of balance where alien life could bloom. As our understanding deepens, so does our sense of wonder. Scientists are developing next-generation telescopes like the James Webb Space Telescope and the Extremely Large Telescope to search for signs of atmospheres, weather patterns, and possibly even biosignatures on nearby exoplanets. If we're lucky, Proxima b could become one of the first alien worlds where we detect the chemical fingerprints of life, perhaps oxygen, methane, or other gases that hint at biological processes. Even if we never set foot there, Proxima Centauri b reminds us that the universe is full of possibilities. It whispers to us across light years, telling a story written in gravity and starlight. It invites us to imagine strange ecosystems beneath foreign skies and civilizations that may be peering outward just as we are. And so, as you close your eyes and breathe in the silence of deep space, picture Proxima b turning slowly around its crimson sun. Picture mountains rising beneath alien skies, clouds drifting over distant valleys, and the flicker of starlight dancing on an ocean no one has yet seen. Perhaps, in the stillness, you can almost hear the heartbeat of a living world waiting to be discovered. Proxima Centauri b is more than just a planet. It's a mirror, reflecting our hopes, our questions, and our endless longing to understand the cosmos. Its proximity makes it feel like a neighbor, while its mystery reminds us that the universe is still largely unknown. Drifting now among the stars, let your thoughts settle gently on this world, so close in the grand scheme of things, yet still far beyond our reach. One day we may know if life exists there. One day we may reach across the cosmic ocean and touch another shore. TRAPPIST-1F is a distant world orbiting a quiet crimson star, and as we continue our gentle journey through the cosmos tonight, we sail beyond Earth, beyond the moon, and past the orbiting sentinels of our solar system, toward a system of worlds that has captivated astronomers and dreamers alike. About 40 light-years from Earth lies a small, dim star known as TRAPPIST-1, a red dwarf nestled within the watery constellation of Aquarius. Though faint, when viewed from our own skies, this star has become one of the brightest beacons in the search for life beyond Earth. Not because of its light, but because of what circles it. 7 rocky planets, all similar in size to Earth, orbit TRAPPIST, one in a tight celestial formation. Each is a potential harbor for life, but among them, one planet, TRAPPIST-1F, draws our attention like a gentle whisper from the dark. Discovered in 2017 through detailed observations with the Spitzer Space Telescope and the TRAPPIST South Telescope in Chile, TRAPPIST-1F emerged from the faint, rhythmic dimming of starlight. As each planet passed in front of its star, it cast a tiny shadow, and in those patterns, astronomers found the story of a world. TRAPPIST-1F is slightly larger than Earth, with a radius about 1.04 times greater. It completes a full orbit every 9.2 Earth days, dancing close to its parent star. Despite this tight orbit, the cool nature of TRAPPIST-1 means that TRAPPIST-1F lies within the system's habitable zone, a region where temperatures might allow for liquid water to exist on the planet's surface. And so, we begin to imagine. Picture a world where the sun is not golden but soft red, suspended low in the sky, never moving, always glowing. If TRAPPIST-1F is tidally locked, as we believe many of its sister planets are, then one side of the planet always faces the star in unending daylight, while the other remains cloaked in eternal night. But between these extremes, along the terminator, the twilight band dividing day and night, a sliver of land or sea might enjoy a steady, temperate climate. It is here, in the hush of perpetual dusk, that we imagine alien winds rustling across open plains or brushing across calm waters. Perhaps clouds drift lazily overhead, catching the dim red glow of the sky. Perhaps strange tides shift in oceans warmed from beneath by volcanic heat, their chemistry rich and ancient. Maybe deep below the surface, life clings to rocky niches, warmed by the memory of the planet's creation. TRAPPIST-1F may be home to oceans, though we cannot yet confirm it. The planet's lower density compared to Earth suggests a significant amount of water, possibly even more than Earth has. Some models suggest it could be a true water world, with deep global seas stretching endlessly in all directions, hiding a surface no one has ever seen. If such oceans exist, and if the planet possesses an atmosphere, and there are hints that it might, then it could support a stable climate, allowing the water to remain liquid and the temperatures to stay mild. And where there is water, there may be life, however humble, breathing quietly beneath alien waves. The planet's slow, rhythmic orbit and gravitational interactions with its siblings create a harmonious resonance. Each planet in the TRAPPIST-1 system gently tugs on its neighbors, creating a kind of cosmic symphony. These regular gravitational pulses have helped scientists refine estimates of each planet's mass and composition with exquisite precision. TRAPPIST-1F is lighter than Earth, and this lower density supports the idea of a watery or icy interior. It may even have a thick atmosphere composed of nitrogen, carbon dioxide, or other greenhouse gases that trap heat and stabilize temperatures across its surface. If so, this could make it one of the most habitable worlds in the entire system, perhaps even more so than its neighbor, TRAPPIST-1e. But this world is not without its challenges. Like all the TRAPPIST planets, it lies close to its volatile parent star. Red dwarfs like TRAPPIST-1 can emit powerful flares, bursts of radiation that could erode atmospheres or damage delicate molecules necessary for life. Yet some scientists believe these early flares may help life form by sparking chemical reactions in an atmosphere rich with the building blocks of biology. If life ever did emerge on TRAPPIST-1F, it may have taken a different path than life on Earth. In a dimmer world bathed in red light, photosynthesis would evolve differently. Plants, if they exist, might be dark, almost black, absorbing every scrap of available light. Animals, or their alien equivalents, might sense their environment through vibrations, temperature, or magnetism adapted perfectly to the rhythm of the world they call home. We don't yet know what secrets TRAPPIST-1F holds, but the James Webb Space Telescope is watching, listening. It may one day detect signs of gases in this planet's atmosphere, oxygen, methane, water vapor, or carbon dioxide, molecules that could hint at processes biological or geological in nature. Even the absence of these gases could teach us something profound. As you breathe slowly now, wrapped in the quiet of this moment, let your thoughts drift to this distant world. 40 light years from Earth, a planet circles a cool, ancient sun. It moves in harmony with 6 other worlds, each pulling gently on the others in an endless, silent waltz. TRAPPIST-1F may be alone, or it may be teeming with life forms we cannot imagine. But whether it's a barren ocean world or a cradle of alien biology, it reminds us that Earth is not alone, that the ingredients for life may be scattered widely across the universe, that we are part of something vast. So rest now. Let the darkness wrap around you like a warm blanket. Feel yourself floating through interstellar space, past clouds of gas and light, beyond comets and dust and memory, to a planet where oceans may sleep beneath a soft, red sky. Kepler 186f is a quiet wanderer in the darkness, an Earth-sized planet circling a dim red star some 500 light-years from Earth, nestled in the constellation Cygnus, the celestial swan. It was the first confirmed Earth-sized planet found within the habitable zone of another star. And though the sky it lies under is not like ours and its sun glows red instead of gold, Kepler 186f may not be so different from home. Discovered in 2014 by NASA's Kepler Space Telescope, this planet marked a turning point in our search for other Earths. Before this discovery, we had seen many large gas-wrapped worlds and hot rocky spheres circling close to their stars. But Kepler 186f offered something else, a small, likely rocky planet, comfortably distant from its star, in a zone where temperatures could permit the presence of liquid water. A world, in other words, where life, if it exists, might stand a chance. Imagine now that you are floating above this planet. It is only about 10% larger in diameter than Earth, with a surface gravity that would feel familiar beneath your feet. The star it orbits, Kepler 186, is a red dwarf, cooler and fainter than our own sun. This means Kepler 186f orbits much closer to its star than Earth does, but not too close. It completes one orbit every 130 days, staying just far enough away to receive about 1/3 the sunlight Earth gets. Under such a dim sun, the days will be long and shadowed. The sky, if the planet has an atmosphere, might glow faint red or copper even at midday. Plants, if they exist, would need to adapt to this cooler light. On Earth, we see green because plants reflect green light and absorb the rest for photosynthesis. On Kepler 186f, if life evolved in similar ways, plants might appear black or deep crimson, drinking in the red light to fuel their growth. Scientists believe Kepler 186f is likely rocky. This is based on its size, which is close to Earth's, and its density, though we haven't yet directly measured it. But all the best models suggest it's a solid planet, not a gas giant or an ice world. And because it sits in the habitable zone, the region around a star where liquid water can exist, it has a real chance of being what we call potentially habitable. But what would that habitability mean for life? Much depends on whether Kepler 186f has an atmosphere, and what that atmosphere might contain. The red dwarf star it circles is known to be less active than some of its more volatile cousins. That's good news, because many red dwarfs can send out flares and harsh radiation, stripping the atmospheres from nearby planets. If Kepler 186f formed with a thick enough atmosphere, and if its star has remained relatively calm over billions of years, the planet might have kept that protective shield. It might still today cradle clouds, wind, even rain. Imagine now the surface beneath that sky. The land may be scarred by ancient rivers or shaped by glaciers long melted. Perhaps it has vast plains of iron-rich rock or towering mountains cloaked in frost. If oceans exist, they may be deep and dark, reflecting the ruddy light from above in shimmering hues of garnet and gold. Kepler 186f may also be tidally locked to its star, meaning one side always faces the light, while the other is wrapped in endless night. On such a world, the line between day and darkness, the terminator, could be a band of constant twilight. This twilight zone may offer the most stable temperatures, where ice melts, clouds form, and ecosystems, if they exist, could thrive. We do not know yet if Kepler 186f has oceans, or if it has air, or if its story includes even the simplest forms of life. But what we do know is that it exists, and that its discovery was a lighthouse moment for planetary science. It showed us that Earth-sized planets in habitable zones are not rare. They are part of the cosmic tapestry. They are out there, waiting. Since 2014, thousands of other planets have been discovered, many in habitable zones. But Kepler 186f holds a special place. It was the first of its kind, a pioneer, whispering to us that the galaxy may be full of hidden Earths, quietly circling stars we'd never thought to notice. The atmosphere of Kepler 186f, if one exists, might someday be studied with more powerful telescopes. Instruments like the James Webb Space Telescope and future observatories beyond it may one day detect the spectral fingerprints of gases like oxygen, carbon dioxide, or even methane. The presence of these biosignatures could suggest something stirs on this distant world, something alive, metabolizing, changing the air over time. Even without such proof, though, Kepler 186f invites us to dream. As you drift tonight towards sleep, think of that planet turning slowly under its red sun. Think of alien winds stirring quiet seas, or perhaps curling through forests of dark, leaf flora, evolved in ways we cannot yet imagine. Think of the patient rhythm of a world that may have been forming life long before life took hold here on Earth. Kepler 186f is old, estimated to be over 4 billion years of age. That is plenty of time for complexity to rise from simplicity, for chemistry to blossom into biology, for evolution to play its long and winding game. If life began there, it has had time to grow, to adapt, to stretch toward the pale red light and find its own way of being. And if no life exists, then it is still beautiful. A quiet world, circling a modest star, holding steady in the vacuum of space. A reminder that not all miracles require an audience. So let yourself rest now. Let the thoughts of distant red suns and alien forests settle softly around you like a blanket. You are connected to something vast, the search, the wonder, the questions we send like lanterns into the dark. Sleep gently tonight, knowing that Kepler 186f turns quietly on, far from here, beneath a twilight sky, and that in the silence of space you are never truly alone. Gliese 581d is a potentially rocky exoplanet orbiting the red dwarf star Gliese 581, located approximately 20.3 light-years from Earth in the constellation Libra. First discovered in 2007 via the radial velocity method, Gliese 581d was one of the earliest exoplanets considered potentially habitable. Its mass is estimated to be about 6.98 times that of Earth, placing it in the super-Earth category. Though its existence was briefly debated due to uncertainties in the signal, reanalysis of the data has since reestablished it as a confirmed planet in the Gliese 581 system. Gliese 581d orbits its star at a distance of roughly 0.22 AU, which is farther than any of the other known planets in the system. However, because Gliese 581 is an M-type red dwarf with only about 1.3% of the Sun's luminosity, the planet lies near the outer edge of the star's habitable zone. It receives about 30% of the solar flux that Earth receives from the Sun. While this is considerably less than what Earth gets, it is still within the range where liquid water could theoretically exist. if the planet has a sufficiently thick and insulating atmosphere to trap heat through the greenhouse effect. The estimated orbital period of Gliese 581d is about 66.6 Earth days. Due to its proximity to the host star and the slow rotation typical for such planets, Gliese 581d is thought to be tidally locked or in a spin-orbit resonance, with one side constantly facing the star. This would create extreme temperature differences between the day side and the night side. However, if the planet possesses a dense atmosphere, it could redistribute heat efficiently enough to create stable conditions across at least part of the surface. Atmospheric modeling has played a crucial role in evaluating Gliese 581d's habitability. Early models suggested that if the planet had a dense carbon dioxide atmosphere, on the order of 5 to 10 bars, it could trap enough heat to support surface temperatures above the freezing point of water. These models show that even with reduced sunlight, a more rich atmosphere could maintain a stable climate, especially in regions facing the star or along the terminator zone. If the atmosphere were even thicker, the greenhouse effect could be stronger, possibly making large portions of the surface temperate. However, this hinges entirely on whether Gliese 581d has an atmosphere at all. No direct measurements of its atmospheric composition or pressure currently exist, and the planet does not transit its star, which prevents the use of transmission spectroscopy. Nonetheless, its substantial mass suggests strong gravity, which would favor the retention of an atmosphere over geological timescales, particularly if it had a magnetic field to protect against stellar wind erosion. Red dwarfs like Gliese 581 are known for emitting strong stellar flares and high-energy radiation, particularly during their early evolution. These flares can strip atmospheres from planets that lack magnetic protection. However, Gliese 581 is considered a relatively quiet and mature red dwarf, reducing, but not eliminating, the likelihood of severe atmospheric erosion if the planet formed with a substantial atmosphere or outgassed it from volcanic activity, and if it avoided significant stripping during its host star's active youth, then it might still retain enough atmospheric mass to support surface habitability. From a compositional standpoint, Gliese 581d is likely to be a rocky planet with a solid surface. Models of planetary formation in M-dwarf systems suggest that planets in the super-Earth mass range tend to form with silicate mantles and iron cores, though some may also acquire significant amounts of volatiles. If Gliese 581d formed farther out in the system and migrated inward, it may have brought water and ices with it. This raises the possibility of surface or subsurface oceans, depending on temperature and pressure conditions. Without a precise radius measurement, it's impossible to determine the planet's bulk density and, by extension, its composition. However, if it is truly rocky, its surface gravity would be roughly twice that of Earth's, influencing everything from atmospheric retention to potential biological processes. The increased gravity would also make mountain ranges lower and oceans shallower compared to Earth, but could still allow for diverse terrains and potential habitats. Chemical conditions are another key consideration. For life to exist as we know it, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur must be present and available. These elements are widespread in planetary systems and likely present on Gliese 581d, but whether they are accessible at the surface or in biologically usable forms is unknown. The atmosphere, if present, could provide some of these elements in gaseous form or through deposition onto the surface. Energy availability is another major question. Life on Earth depends primarily on sunlight, but in low-light environments like the outer edge of a red dwarf's habitable zone, photosynthesis would be less efficient. Organisms would need to adapt to lower photon flux, possibly using different pigments or energy pathways. Alternatively, life could rely on chemosynthesis, drawing energy from chemical gradients created by geological or atmospheric processes, such as volcanic activity or hydrothermal vent systems. If Gliese 581d has tectonic activity, as suggested by its mass and likely internal heat, such energy sources could be present. The presence of liquid water is critical. Climate simulations have shown that with an atmosphere at least 5 times thicker than Earth's and composed primarily of SO, Gliese 581d could maintain surface temperatures above 273 K 0 degrees Celsius. Liquid water could persist in regions facing the star or in basins where heat and atmospheric pressure converge. If the atmosphere includes water vapor, this would further amplify the greenhouse effect and increase the stability of liquid water. However, in the absence of a thick atmosphere, surface temperatures could be too cold, freezing out any water and rendering the planet sterile. The planet's long orbital period and potential spin-orbit resonance could influence seasonal cycles, wind patterns, and ocean currents, if oceans exist. These factors would all affect climate stability and, by extension, habitability. A stable climate with a global or regional hydrological cycle would support the idea of long-term habitability, potentially allowing life to emerge and evolve. No biosignatures have been detected on Gliese 581d, nor is there any direct evidence for life. Current observational technologies are not sensitive enough to analyze the atmospheric chemistry of non-transiting exoplanets like this one. Until telescopes capable of high-resolution spectroscopy are deployed, the question of life on Gliese 581d will remain theoretical. In summary, Gliese 581d is a super-Earth with several characteristics that make it a strong candidate for habitability. It orbits near the outer edge of the habitable zone of a relatively stable red dwarf, likely has a rocky composition, and may retain a thick atmosphere capable of supporting surface liquid water. Climate models show that with the right conditions, particularly a dense CO atmosphere, temperatures could remain within a habitable range. However, the lack of direct measurements of its atmosphere, surface conditions, or chemical composition means that its potential for life remains an open and unconfirmed possibility. Whether it is a frozen wasteland, a runaway greenhouse world, or a temperate planet with oceans and weather systems, Gliese 581d remains one of the earliest and most enduringly intriguing targets in the search for extraterrestrial life. Ask ChatGPT. Kepler 452b is a confirmed exoplanet orbiting the G-type star Kepler 452, located approximately 1,800 light-years from Earth in the constellation Cygnus. Announced by NASA in 2015, it gained attention for being the first Earth-sized planet discovered within the habitable zone of a star that is nearly identical to our Sun. Due to its size, orbit, and stellar similarity, Kepler 452b was quickly nicknamed Earth's older cousin. Though intriguing, its true potential to support life remains uncertain due to a lack of direct data about its atmosphere, surface conditions, and mass. The host star, Kepler 452, is classified as a G2 type main sequence star, virtually the same type as our Sun. It has about the same temperature and spectral class, but is older, estimated at around 6 billion years. This stellar maturity suggests that its planets have had more time for environmental and possibly biological evolution. Kepler 452 is about 20% brighter than the Sun and has a slightly larger radius, affecting the position of its habitable zone. Kepler 452b orbits this star at a distance of roughly 1.05 astronomical units AU, very similar to Earth's distance from the Sun, and completes one orbit every 384.8 Earth days. It receives around 10% more stellar energy than Earth does, placing it within the inner part of Kepler 452's habitable zone. This level of solar flux is significant because it may push the planet toward the warmer edge of habitability. If the planet has Earth-like conditions, the increased insolation might be enough to slowly drive climate changes over geological timescales. In terms of size, Kepler 452b has a radius approximately 1.6 times that of Earth. This places it in the range between Earth and mini-Neptunes. While this size suggests it might be rocky, it's also possible that it could have a substantial volatile envelope. Statistical models of planets this size suggest that there's about a 50 to 60% chance Kepler 452b is terrestrial rather than gaseous, without a measured mass or density. Since the planet does not transit frequently enough for follow-up confirmation, its composition remains speculative. Assuming Kepler 452b is rocky, its gravity would be stronger than Earth's, perhaps about 1.5 to 2 times greater depending on its exact mass. This would allow the planet to retain a thick atmosphere over billions of years and support climate stability. Stronger gravity could also influence weather patterns, ocean depths if oceans exist, and mountain formation, creating a world that's familiar yet fundamentally different in its geological features. Kepler 452b's stellar environment adds another dimension. With a host star 1.5 billion years older than the Sun, the planet has had significantly more time for evolutionary processes to unfold. On Earth, life went from single-celled organisms to complex multicellular life over a span of billions of years. If Kepler 452b began with similar ingredients, liquid water, a stable environment, essential elements, life could have had a much longer timeline to evolve and diversify. However, that same stellar age could also imply a risk. As stars age, they grow brighter. Kepler 452 is already about 20% more luminous than it would have been during its early life. If Kepler 452b has been within the habitable zone for over 6 billion years, it may now be entering a phase similar to what Earth will face in its distant future, a slow, progressive warming that threatens climate stability. This could cause increased water evaporation, leading to a moist greenhouse effect, and eventually to the complete loss of surface water. Whether this runaway heating has occurred or is underway depends entirely on atmospheric composition and feedback mechanisms. A planet with robust carbon cycling, cloud cover, and reflective surfaces could remain temperate for a long time, whereas a thinner or poorly regulated atmosphere could tip the balance toward uninhabitable conditions. Without atmospheric data, the presence or absence of water on Kepler 452b is purely theoretical. If it formed with a water inventory comparable to Earth's and retained it across billions of years, it might possess oceans, lakes, and rivers, potentially supporting life as we know it. If it lost its water early on, either through impact, stripping, ultraviolet photodissociation, or stellar wind, it could now be a dry, rocky world more like Venus. If it has too much water, such as being a water world with a deep global ocean, it might lack the land-based weathering cycles necessary to regulate climate through carbon-silicate feedback. If the planet is instead more Neptune-like, with a thick hydrogen and helium envelope, then surface habitability would be unlikely. Such a world might have high pressures and temperatures beneath its clouds, with conditions too extreme for life as we understand it. But if it's a borderline case, a rocky planet with a dense but manageable atmosphere, it might have an Earth-like or even super-Earth climate system capable of supporting biology. Life, if it exists or once existed on Kepler 452b, would need to adapt to a range of environmental differences, stronger gravity, possibly greater UV radiation from a more luminous star, longer years, and perhaps higher surface temperatures. Photosynthetic organisms might have evolved pigments optimized for slightly different light conditions. If the planet has continents and oceans, weather systems might be stronger or slower, depending on rotational dynamics and atmospheric density. Because the planet does not frequently transit its star and is extremely distant, current technology cannot probe its atmosphere or surface directly. No measurements of chemical composition, cloud cover, pressure, or biosignatures are available. It remains inaccessible to even advanced telescopes like the James Webb Space Telescope. However, Kepler 452b remains a prime target for future missions capable of direct imaging or high-resolution spectroscopy, particularly those that could detect oxygen, methane, or other signs of disequilibrium that might indicate biological processes. Kepler 452b's discovery also carries philosophical weight. It represents one of the closest analogs to Earth discovered so far in terms of size, orbit, and stellar environment, albeit older and more evolved. It offers a glimpse of what Earth's future could resemble and invites speculation about whether civilizations, or even microbial life, might once have emerged there, evolved, and possibly perished long before humans ever looked toward the sky. In summary, Kepler 452b is a planet of extraordinary interest. It orbits a near-Sun twin in the habitable zone, has a size close to the transition between rocky and gaseous worlds, and may have had billions of years to host stable surface conditions. Its true nature, rocky or gaseous, dry or oceanic, sterile or alive, remains unknown. But based on what we do know, it stands as one of the most compelling candidates in the ongoing search for life beyond our solar system. Kepler 442b lies far beyond the reach of our telescope's direct gaze, over 1,200 light-years away in the direction of the constellation Lyra. It is a distant world orbiting a quiet orange dwarf star, ancient and steady, with a name that evokes precision and discovery, Kepler 442. Tonight, we drift there together, not with rockets or ships, but with curiosity and quiet imagination. This world was first revealed to us in 2015 by NASA's Kepler Space Telescope, which stared at one narrow patch of sky for 4 years. It watched for subtle dimming of starlight, those telltale dips that occur when a planet passes in front of its host star. Out of over 150,000 stars, Kepler detected a few thousand of these shadows, and one of the most promising among them was Kepler 442b. It is what we call a super-Earth, slightly larger than our planet, with a diameter about 1/3 greater and a mass possibly 2 to 3 times higher. These dimensions suggest a rocky surface rather than one of gas or ice, and its orbit, just right for the modest warmth of its orange sun, places it within the habitable zone, a celestial sweet spot where conditions might allow liquid water to pool on the surface. Let that sink in, a rocky world bathed in gentle orange light, receiving just enough warmth to keep oceans from freezing or boiling away. It may not be Earth, but it is Earth-like enough to stir our imagination and our hope. If you could stand there on Kepler 442b, you might find gravity a little stronger, the air a little denser. The sky above would be painted in warmer hues than we know. Its star, smaller and cooler than our own, would shine like a copper coin hung low in a golden sky. Because orange dwarfs burn more slowly than our sun, Kepler 442, the star, may lie for tens of billions of years, far longer than Earth's own bright host. This longevity is one reason scientists consider planets like Kepler 442b such hopeful places for life to begin and endure. The planet completes an orbit every 112 Earth days, its year passing by faster than ours, though time might feel slower beneath such a still and stable sun. If Kepler 442b is tidally locked, as many close-orbiting exoplanets tend to be, then one side would forever face its star, drenched in endless daylight, while the far side would sleep in perpetual night. But between these two extremes, along the gentle curve of twilight, conditions might be just right, not too hot, not too cold, a land of eternal dusk where oceans might shimmer under burnt orange skies. This band, known as the Terminator Zone, is where many scientists believe life could flourish. Winds would circulate from the hot side to the cold, creating temperate climates and possibly driving ocean currents. Rain might fall. Rivers could flow. Storms might whisper across canyons and forests that we cannot yet see. But could life really exist there? We do not know, but the signs are encouraging. Kepler 442b is large enough to hold an atmosphere. And unlike planets orbiting red dwarfs, stars that often emit dangerous flares, Kepler 442's host star is relatively calm. Less radiation. More consistency. A better chance for fragile molecules to link, replicate, evolve. Some researchers believe Kepler 442b has one of the highest Earth Similarity Index scores of any known exoplanet. It is distant, yes, and it may not be accessible in our lifetime, but based on size, orbit, stellar stability, and location in the habitable zone, it stands among the most promising candidates for alien life in the observable universe. Its distance, though vast, is not insurmountable. Every photon of light we gather from Kepler 442b, every faint glimmer, carries with it information about its atmosphere, about its temperature, about its potential to nurture life. Future telescopes like the James Webb Space Telescope and its successors are already peering deeper into the cosmos, examining the light from distant stars as it passes through their planet's atmospheres. With this method, known as transit spectroscopy, we may one day detect the signatures of life: oxygen, water vapor, carbon dioxide, methane, all clues that biology could be shaping the air. And even if Kepler 442b turns out to be barren, it still teaches us something beautiful: that Earth is not the only world of its kind, that the cosmos does not build its planets by accident or in isolation, that across the darkness of space, there are others, waiting, turning, shining softly beneath alien suns. So let us linger here a moment longer, drifting over its imagined landscape. Perhaps there are mountains, tall and windswept, casting long shadows into valleys of red moss or frost. Perhaps there are oceans, thick with minerals, their tides pulled by unseen moons. Perhaps, beneath its surface, there are warm places, pockets of geothermal heat, where chemistry simmers in dark caverns slowly, patiently, forming the building blocks of life. And perhaps there are eyes that have already opened there, blinking in the golden light, wondering about the stars, wondering if they are alone. Tonight, as we rest, we are connected to this distant world by something stronger than gravity, by our shared place in the universe. A planet orbits a quiet star 1,200 light years from here, and we, tiny and fragile, reach out to it with questions and dreams. Kepler 442b does not know we are watching, but still, it turns. Still, it endures. And in that turning, in that quiet resilience, we see a reflection of our own world, our own hopes. Wolf 1061c is a rocky exoplanet orbiting the red dwarf star Wolf 1061, located approximately 13.8 light years from Earth in the constellation Ophiuchus. Discovered in 2015 through the radial velocity method, Wolf 1061c is the second of 3 known planets in the system and is one of the closer potentially habitable exoplanets known to date. It orbits its star every 17.9 Earth days and has a minimum mass of about 4.3 Earth masses, placing it firmly in the category of a super-Earth. Wolf 1061c lies near the inner edge of its star's habitable zone. The habitable zone is the region around a star where a planet could potentially have the right surface temperatures for liquid water, assuming an atmosphere of suitable composition and pressure. Wolf 1061c receives about 60% more stellar radiation than Earth does from the Sun. If it lacks a significant atmosphere or has low albedo surface reflectivity, surface temperatures could be extremely high. However, with a reflective atmosphere and sufficient cloud cover, models suggest the planet could still fall within the range of potential habitability. Its host star, Wolf 1061, is a relatively quiet M3 type red dwarf with a mass about 0.25 that of the Sun and only 2% of its luminosity. Because red dwarfs emit less visible light, but often more radiation in the infrared and ultraviolet bands, the climate behavior of planets orbiting them can be complex. Wolf 1061 itself has shown relatively low levels of stellar flare activity compared to other red dwarfs, which may reduce the atmospheric stripping or surface sterilization that can occur on planets around more volatile stars. This contributes to the idea that Wolf 1061c could retain an atmosphere over long periods of time, though direct evidence for such an atmosphere has not yet been obtained. The size and mass of Wolf 1061c suggests that it has a strong gravitational field, likely allowing it to hold onto a substantial atmosphere if one developed. Whether this atmosphere exists and what it's composed of remains unknown due to the limitations of current observational technology. Since the planet was not discovered through the transit method, we lack data on its radius and atmospheric composition. However, assuming an Earth-like composition, the surface gravity would likely be stronger than Earth's, which could favor atmospheric retention and climate stability. Given its proximity to its star, Wolf 1061c is very likely tidally locked. This means that one side of the planet always faces the star while the opposite side is perpetually dark. In a tidally locked world, Temperature differences between the star-facing side and the dark side can be extreme, possibly creating uninhabitable zones. But if Wolf 1061c has a thick atmosphere or oceans, heat could be circulated around the planet, moderating temperatures and potentially creating a habitable band in the twilight zone where the sun is always near the horizon. To evaluate its potential for life, several planetary and orbital factors must be considered. The first is orbital eccentricity. Wolf 1061c appears to have a moderately elliptical orbit, which would cause fluctuations in surface temperature over the course of its year. This variation might limit habitability unless the planet has a robust atmosphere or thermal inertia such as oceans to buffer those changes. Climate models suggest that planets with fluctuating orbits can still be habitable, but the extremes must be mitigated by atmospheric or geological processes. In terms of internal composition, Wolf 1061c is almost certainly rocky. At over 4 Earth masses, it may possess a larger iron core and thinner mantle compared to Earth. This could influence tectonic and magnetic activity. A magnetic field would be particularly valuable for deflecting harmful stellar particles and protecting any atmosphere from being stripped away. However, whether a magnetic dynamo is present cannot be known without direct measurements. Another question is the presence of water, either on the surface or beneath it. Since Wolf 1061c does not transit its star, we lack data on its albedo, atmospheric thickness, or surface conditions. If it formed in the outer system and migrated inward, it could have retained significant volatiles, including water. Alternatively, if it formed in situ near its current position, it may have been exposed to higher stellar radiation in its early years, potentially drying it out. Simulations by some researchers suggest that Wolf 1061c might be too close to the inner edge of the habitable zone, leading to a runaway greenhouse effect similar to Venus. Under such a scenario, any water would evaporate and the planet would become hot and hostile with a dense COO-rich atmosphere. On the other hand, different climate models, especially those that assume high reflectivity or cloud feedback, indicate that parts of the planet could remain cool enough for liquid water to exist. Without direct atmospheric measurements, both scenarios remain possible. From the standpoint of chemistry, life requires more than just water and temperature. Essential elements like carbon, nitrogen, sulfur, phosphorus, and oxygen must be present and accessible. These elements are common in the galaxy and likely present in the protoplanetary disk from which Wolf 1061c formed, but their availability on the surface or in the atmosphere is unknown. Additionally, the energy gradient needed for metabolic processes, sunlight, chemical imbalances, or geothermal heat would also be essential. If the atmosphere is too thick or the surface pressure too high, sunlight might not reach the surface in usable forms, complicating surface habitability. Despite the uncertainties, Wolf 1061c ranks highly on several Earth Similarity Index (ESI) and habitability metrics. This makes it a strong candidate for further study, especially as new telescopes become available. The planet's close proximity to Earth enhances its observational accessibility. Future missions equipped with high-resolution spectrometers, whether space-based or ground-based, could look for biosignature gases like oxygen, methane, ozone, or nitrous oxide, which, if found together in disequilibrium, could be strong indicators of biological activity. However, as with all exoplanets, it is critical to remember that habitability is not the same as inhabited. A planet can exist in the perfect temperature range, have a stable orbit and even liquid water, and still be devoid of life. Sterilizing radiation events, unfavorable surface chemistry, or lack of long-term geological cycling could prevent life from ever taking hold. On the other hand, even if conditions are marginal, life could arise and adapt in forms very different from those on Earth. In conclusion, Wolf 1061c presents a compelling case for potential habitability. It is massive enough to retain an atmosphere, close enough for detailed observation, and located near the habitable zone of a relatively stable red dwarf. It may have retained liquid water, and models suggest it could have regions where life as we know it could survive. But without direct evidence, such as atmospheric spectra or biosignature detections, its status remains uncertain. Whether Wolfton 61c is a barren, overheated world or a temperate super-Earth with oceans and clouds will depend on future observations and continued refinement of planetary climate models. For now, it remains one of the most intriguing nearby worlds in the search for alien life. Ross 128b circles in silence around a quiet ancient star just 11 light-years away from Earth in the direction of the constellation Virgo. It is a world unseen by our eyes but glimpsed through the delicate wobble of its parent star. Among the thousands of known exoplanets, Ross 128b stands apart, not just for its nearness, but for its calm, its quiet, and the possibility that, even now, it might be harboring life beneath its red-tinged skies. Close your eyes and imagine it, a rocky world similar in size to Earth, orbiting a gentle red dwarf star called Ross 128. This star is smaller and cooler than our sun, and it glows not with brilliant white or yellow, but with the steady, soft crimson of ancient embers. Unlike many red dwarfs, which flare and hiss with violent bursts of radiation, Ross 128 is exceptionally calm, a rare trait in stars of its kind. And that quietness may be the most important gift it offers to its only known planet. Discovered in 2017 using the HARP spectrograph in Chile, Ross 128b was found not by watching its shadow cross the star, but by listening carefully to the star's movements. When the planet orbits, it gently tugs on its star, creating a subtle Doppler shift in the star's light. Over many months of observation, that telltale wobble revealed a planet, a small one, likely rocky, with a mass just 1.35 times that of Earth. It orbits very close to its star, completing a full revolution every 9.9 Earth days. But because Ross 128 is so cool and dim, that closeness is not a curse. In fact, it places Ross 128b right on the inner edge of the habitable zone, the region around a star where temperatures might allow liquid water to exist. That narrow orbit is bathed in just enough heat to keep ice from locking the world in eternal frost, and yet not so much that water would evaporate into space. If Ross 128b has an atmosphere, and many scientists believe it could, it might act like a greenhouse, trapping just enough warmth to support temperate conditions. The planet might host lakes, rivers, or even shallow oceans glinting under the star's subdued light. Now imagine standing on its surface. The gravity would feel almost identical to Earth's, just a touch heavier. The air, if breathable, might carry the scent of unfamiliar flora. The sky could glow a soft red during the day, fading to deep maroon at night. Shadows would stretch long and dark, cast by a sun that never rises high but lingers low and warm. It's possible that Ross 128b is tidally locked, always showing the same face to its star, one side bathed in endless daylight, the other in frozen dark. But along the line between those extremes, the terminator zone, a perpetual twilight could exist. There, the temperature might be just right. The atmosphere, if thick enough, could circulate warmth around the planet, distributing heat and allowing for climates that support life. One of the reasons Ross 128b excites scientists is the nature of its star. Red dwarfs are the most common stars in our galaxy, and most of the planets in the habitable zone around them tend to be bombarded by flares and radiation. This often strips away atmospheres and makes life difficult or impossible to sustain. But Ross 128 is an older, quieter star. It spins more slowly and emits fewer flares. In stellar terms, it's peaceful, an ideal environment for life to begin and persist. What we don't yet know are the fine details. Does Ross 128b have an atmosphere? Does it contain water? Are there gases like oxygen or methane that might suggest the presence of life? These are questions the next generation of telescopes is designed to answer. With powerful instruments like the James Webb Space Telescope and observatories soon to follow, we may one day detect the chemical fingerprints in its atmosphere, using a method called transmission spectroscopy. If we find evidence of life, biosignatures that don't come from geology alone, it will mark one of the most profound discoveries in human history. But even now, in the stillness of the present, Ross 128b offers something beautiful. Its nearness, just 11 light years away, makes it one of our closest potentially habitable neighbors. It's not the far distant whisper of a planet thousands of light years away. It's a near voice, a quiet signal from the cosmic neighborhood reminding us that Earth may not be the only cradle of life. As we drift into sleep tonight, imagine a world of gentle winds and red skies, turning slowly under the watch of a peaceful star. Perhaps beneath its surface are warm aquifers or seas where primitive life has found shelter from solar storms. Perhaps in its quiet oceans, single-celled organisms drift through darkness, just as they once did on Earth. Or perhaps Ross 128b has advanced far beyond that. Maybe its civilization, if one exists, looks up at a pale blue dot in the sky, our sun, and wonders the same things we do. Are we alone? Is someone watching the stars as we are? Is life as fragile and precious for them as it is for us? But even if life has never stirred there, Ross 128b still matters. It represents what is possible. A rocky world around a quiet star, holding the right ingredients in the right place at the right time. It's not a fantasy. It's real. It exists. And so tonight, as you breathe softly and your thoughts begin to drift, know that out in the dark, just a few steps beyond our solar system, another Earth-like world is waiting in silence, waiting for us to learn more, waiting perhaps for us to arrive. Let your imagination float there through the quiet dark across 11 light years of soft eternal night until you land gently beneath its red sky. You are not alone in the universe, not in wonder and not in the longing for connection. TRAPPIST-1e is one of the most promising worlds we've ever found in the search for alien life, and tonight, under the soft, dark canopy of stars, we drift once again into the quiet of the cosmos to visit this distant, mysterious planet. Nestled about 40 light years away from Earth in the constellation of Aquarius, TRAPPIST-1e orbits a dim, cool red dwarf star named TRAPPIST-1, a star that has quietly captured the attention of astronomers across the world. TRAPPIST-1 is not large or bright, but what it lacks in luminosity, it makes up for in company. This single star is home to at least 7 Earth-sized planets, all nestled closely together in orbits tighter than Mercury's around our sun. And among them, TRAPPIST-1e stands out like a jewel in the dark. Discovered in 2017 through a careful study of tiny dips in starlight, what astronomers call transits, TRAPPIST-1e was one of the later additions to this extraordinary planetary system. Using the Spitzer Space Telescope and ground-based observatories around the globe, scientists noticed the gentle, rhythmic dimming of the star's light caused by planets passing in front of it. With each flicker, a new world revealed itself. And TRAPPIST-1e, with its Earth-like size and its orbit deep within the star's habitable zone, immediately stirred the imagination. This planet is thought to be rocky, solid beneath your feet if you could ever stand there, and just a bit smaller and denser than Earth. It orbits its parent star once every 6 Earth days, which means its year is brief, but not frantic. And though the star it orbits is far cooler than our own sun, TRAPPIST-1e sits at just the right distance to receive a similar amount of energy as Earth does, suggesting that, under the right conditions, it could support liquid water on its surface. And so, in the mind's eye, we begin to imagine this faraway world. Picture a landscape bathed in gentle red light, not harsh or blinding, but soft, diffused through a sky tinged with rose and lavender. The star above would appear much larger in the sky than our sun does on Earth, hovering low, glowing with a steady pulse. There are no long sunrises or slow sunsets here. TRAPPIST-1e may be tidally locked, always showing one face to its star. One side may bask in endless daylight, while the other rests in eternal night. And in between, in that temperate zone where day meets night, conditions may be just right, mild, balanced, and possibly habitable. Scientists believe that TRAPPIST-1e might have retained a significant atmosphere, one that could protect its surface from harmful radiation and allow water to remain liquid. And water, as we know, is one of the key ingredients for life. If there are oceans on this world, they may stretch silently beneath alien skies, reflecting the copper glow of a red dwarf sun. If there are winds, they might carry traces of chemistry unlike anything we've ever known. Unlike many other exoplanets we've found, TRAPPIST-1e is not just potentially habitable, it also exists within a family of planets that are equally fascinating. Its neighboring worlds, some slightly warmer, some slightly cooler, orbit together in a delicate dance of gravitational harmony, like pearls strung on invisible threads of motion. This resonance means the planets pull gently on one another, keeping time with each other in a cosmic rhythm that has lasted for billions of years. Such stability is rare, and it gives TRAPPIST-1e a kind of serenity, an orbital grace that may have allowed life, if it exists, to flourish undisturbed over unimaginable spans of time. Future telescopes like the James Webb Space Telescope, which has already begun to peer into alien atmospheres, may one day give us more than theories and numbers. They may detect the faint signatures of molecules drifting high above the surface of TRAPPIST-1e, carbon dioxide, water vapor, ozone, or perhaps methane. These gases could whisper of geology, chemistry, or biology. They could be signs of a living world breathing slowly in the shadows of a dim star. What would life look like there? We cannot know, but the rules of nature would be different under a red dwarf sun. Photosynthesis, if it exists, might have adapted to the crimson light. Plants, if there are any, might be black, dark blue, or even copper-colored, absorbing every drop of precious energy from the feeble starlight. Creatures, if they roam this world, might navigate by magnetism, sound, or subtle shifts in pressure, living in a place where daylight never changes and the stars never move. Yet even if TRAPPIST-1e is barren, with nothing more than rocks and ice and wind, it still offers us something profound perspective. It reminds us that Earth is not unique in its shape or size or orbit. It tells us that our solar system is not alone in having planets that could harbor life. And it opens a window, just a crack, onto the deep, mysterious vastness of space. As you lie back, wrapped in stillness, allow your thoughts to drift outward once more. Beyond the reach of the moon, past the distant glow of Jupiter, through the Kuiper belt, and out into the interstellar night. 40 light years away, a world spins slowly around a dim red sun. It is quiet there, unseen, untouched, but not unknown. TRAPPIST-1e is waiting. Whether it hosts forests or oceans, deserts or ice, it stands as one of our best hopes in the search for alien life. A place where biology might arise not just as a miracle, but as a pattern. A place that reminds us that life, like light, might find a way, even in the darkest corners of the galaxy. And now, in the silence between the stars, let your mind rest on this ancient world. Let your imagination wander over its ridges and plains, through the dusky twilight zone where life might bloom. Feel the rhythm of its orbit, the hush of its winds, the steady light of its star. TRAPPIST-1e is one of the most intriguing exoplanets orbiting a small, quiet star in the constellation of Aquarius. And tonight, we journey gently toward this distant world, sailing softly through the dark, quiet sea of space. Far from the warmth of our sun, 40 light-years away, the TRAPPIST-1 system waits like a cluster of pearls scattered around a single dim ember. At the heart of this system is a red dwarf star, ancient and calm. Though small and faint compared to our own sun, TRAPPIST-1 has become one of the most studied stars in the galaxy, not for what it is, but for what surrounds it. 7 Earth-sized planets orbit this unassuming star, packed closely together in a rhythmic cosmic dance. Among them, TRAPPIST-1e is the second farthest from its parent star, and also one of the largest. It's a planet with gravity just slightly stronger than Earth's, wide and heavy enough to hold onto an atmosphere, possibly even an ocean world bathed in eternal twilight. Discovered in 2017 by NASA's Spitzer Space Telescope in collaboration with the ground-based TRAPPIST Observatory, TRAPPIST-1e revealed itself through the careful observation of tiny dips in starlight, moments when it passed between its star and our telescopes, briefly blocking the light. From these delicate flickers, astronomers were able to estimate the planet's size, mass, and orbit. TRAPPIST-1G is larger than Earth, with a radius about 1.1 times that of our planet. It completes an orbit every 12.3 Earth days, a short year by our standards, yet long enough in the star's gentle warmth for stability. Its distance places it near the outer edge of the star's habitable zone, a region where under the right conditions, liquid water might still exist, and with water comes possibility, not certainty, but potential. A chance, however small, that this world could harbor life. Now, close your eyes and imagine standing at the edge of a vast alien sea. The sky above is dim and dusky, not black, not blue, but colored with the quiet rust-red glow of a distant sun. That sun hangs in the same spot in the sky, never rising, never setting. For if TRAPPIST-1G is tidally locked, as we suspect it is, then one hemisphere always faces the star, forever bathed in daylight, while the opposite side remains in frozen shadow. Between them lies a twilight ring, a thin band around the planet where the sun hovers on the horizon, an eternal dusk where temperatures might be mild, winds might blow gently, and strange life, if it exists, might thrive in the calm. TRAPPIST-1G may be a water-rich world, possibly covered in global oceans with no land at all. Its low density suggests that much of its interior could be made of water or ice. If it has an atmosphere, and many scientists believe it could, it might help circulate warmth from the star-lit side to the dark, stabilizing the climate and preventing the oceans from freezing or boiling away. In such a world, life might live beneath the waves, away from the radiation of flares that sometimes erupt from the red dwarf sun. These flares can be powerful, but over the billions of years of TRAPPIST-1G's existence, life might have adapted. Perhaps under the sheltering arms of deep water, strange bioluminescent creatures could drift in darkness, sensing light, sound, and movement in ways our minds can barely grasp. The gravity on TRAPPIST-1G is strong but not crushing. If you could walk along a floating structure or an island shore, you'd feel just a little heavier than on Earth. You'd hear the whisper of the wind, shaped by unfamiliar gases, and taste the strange, dry air, assuming it's breathable and safe. And above you, the sky would not be still. You'd see the silhouettes of the system's sibling planets passing by, larger than our own moon in Earth's sky, moving quickly, some waxing, some waning, all locked in a graceful gravitational waltz. The TRAPPIST-1 system is unique in this way. The planets orbit so closely that if you were standing on TRAPPIST-1G, you could look up and see your planetary neighbors, TRAPPIST-1F, TRAPPIST-1H, and perhaps even TRAPPIST-1E, gliding silently across the sky. They would appear as bright disks, not stars, and their motion would be fast enough to notice within hours. It's a compact system, tightly woven and gravitationally linked. These orbital resonances help us measure each planet's mass and hint at their internal makeup. TRAPPIST-1G's slightly lower density compared to Earth tells us it likely has a thick layer of volatile material, water, ice, or a dense atmosphere. This structure makes it one of the more mysterious planets in the system. We do not yet know if it is rocky beneath, or if the ocean, if it exists, goes down for hundreds of miles. And what of its atmosphere? Scientists are beginning to explore that question using instruments like the James Webb Space Telescope. With it, they hope to detect the presence of key gases, carbon dioxide, water vapor, maybe even ozone or methane. These molecules, especially if they appear together in unexpected combinations, could hint at active geological cycles, or just maybe, the signatures of alien biology. But even if we never find life there, TRAPPIST-1G holds meaning. It's part of a family of planets that shows us how diverse and intricate planetary systems can be. It proves that small stars can host complex solar systems and that Earth-sized planets are not rare jewels, but common stones scattered across the galaxy. Tonight, as we drift further into calm, imagine this: a world of seas under a red sky, glowing softly in the distance. A place where day and night never change. A place not so different in size or gravity from Earth, but wrapped in mystery, shaped by different forces, molded by different time. And in the stillness, let your thoughts follow TRAPPIST-1G on its orbit. Let your mind's eye float above its oceans through clouds and mists over waves that no human has ever seen. Let yourself be held by the peace of its silence. TRAPPIST-1G may never welcome us in person, but in our imaginations, in our science, in our hope, it is already close. It waits patiently in the dark, spinning quietly, a question written in starlight. So close your eyes now. Let the gravity of dreams draw you in. You are floating, gently, softly, between stars, beside a world where oceans may breathe and life may stir beneath the waves. Tau Ceti is an exoplanet orbiting the sun-like star Tau Ceti, located approximately 11.9 light-years from Earth in the constellation Cetus. It was discovered using the radial velocity method, with its detection first announced in 2012 and its signal refined in later studies. The planet is the fourth closest potentially habitable exoplanet candidate outside our solar system and is notable for its Earth-like size and the relatively stable, quiet nature of its host star. Tau Ceti E has a minimum mass of about 4.3 Earth masses and completes an orbit around its star roughly every 163 days. Tau Ceti is a G-type main sequence star, very similar to the Sun in spectral type, mass about 78% of the Sun's and temperature. However, it is notably older, estimated to be around 5.8 to 7 billion years, and has much lower stellar activity, making it one of the most magnetically quiet stars in the solar neighborhood. This stability makes it a promising host for potentially habitable planets, as reduced stellar flaring and ultraviolet output decrease the chances of atmospheric stripping and surface sterilization over time. Tau Ceti E orbits at about 0.55 AU from its star, receiving roughly 1.5 to 1.7 times the solar flux that Earth receives. This places it just inside the inner edge of the traditional habitable zone. As a result, Tau Ceti is likely to experience higher surface temperatures than Earth, potentially making it more comparable to Venus unless mitigating factors like a high albedo or a thin atmosphere are present. Whether Tau Ceti is habitable or not depends heavily on its atmospheric composition, pressure, and reflectivity. A thick atmosphere rich in carbon dioxide and water vapor could trigger a runaway greenhouse effect, pushing surface temperatures far above the boiling point of water. However, if the planet has a thinner atmosphere or significant cloud cover, it could reflect more sunlight and maintain more temperate conditions. The planet's precise climate state remains unknown, as no transits have been observed, and no atmospheric measurements are available. Given its minimum mass and likely rocky composition, Tau Ceti is generally categorized as a super-Earth. Depending on its actual radius, which we cannot measure without a transit, it may have a surface gravity between 1.5 and 2 times that of Earth, capable of retaining a dense atmosphere over billions of years. This gravity would also help maintain surface stability, support a hydrological cycle if water is present, and potentially drive internal geological processes such as plate tectonics or volcanism. Plate tectonics in active geology could be essential for long-term habitability. They enable the recycling of carbon dioxide through the carbonate-silicate cycle, regulate surface temperature, and maintain a magnetic field through a liquid outer core. A magnetic field, in turn, would protect any atmosphere from being stripped by solar wind and shield surface life from harmful radiation. Whether Tau Ceti has a magnetosphere is unknown, but its potential for active geology is enhanced by its mass and presumed rocky nature. From a chemical standpoint, habitability also hinges on the presence of key bioessential elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are thought to be widespread in planet-forming disks, and Tau Ceti's relatively sun-like composition suggests its planets likely accreted from material rich in these ingredients. However, their availability on the planet's surface or in biologically accessible forms depends on the planet's geochemistry and atmospheric evolution. Tau Ceti's position near the inner edge of the habitable zone complicates the likelihood of surface liquid water. Planets in this region face a high risk of entering a runaway greenhouse state, particularly if their atmospheres are dense and water-rich. Earth is just outside this limit, and Venus, a world with a dense COO atmosphere and no liquid water, is often used as a model for planets inside it. Climate simulations of Tau Ceti under various atmospheric scenarios show that depending on cloud behavior, rotation rate, and surface reflectivity, it could potentially retain habitable conditions in specific regions, especially if atmospheric feedbacks act to stabilize surface temperatures. The age and stability of the Tau Ceti system add a layer of intrigue. At nearly 6 billion years old, the system has had ample time for life to emerge and evolve, far longer than life has existed on Earth. If Tau Ceti ever had habitable conditions, it's had billions of years for biology to take root. But time also allows for planetary evolution toward less habitable states. For example, if Tau Ceti began as a warm, wet planet, it could have undergone a moist or runaway greenhouse transition early in its history, boiling away surface water and locking the planet into a hot, arid state. One additional factor to consider is the system's architecture and potential for heavy asteroid bombardment. Tau Ceti is known to have a massive debris disk, several times more massive than our own Kuiper belt, which could indicate a higher rate of asteroid and comet impacts on its inner planets. Frequent impacts could inhibit the development of life or strip away atmospheres, particularly in the early stages of planetary evolution. On the other hand, such impacts could also deliver volatiles, including water and organic molecules, contributing to habitability if the bombardment rate declines over time. No direct biosignatures or atmospheric constituents have been detected on Tau Ceti E, and its non-transiting orbit prevents detailed spectroscopic study with current telescopes. Its potential for life remains entirely theoretical, based on orbital position, mass, and assumptions about atmospheric behavior. Future instruments capable of direct imaging, such as the planned ELT Extremely Large Telescope or space missions like LUV, OIR, or HABEX, could target Tau Ceti for atmospheric characterization, looking for gases like oxygen, ozone, methane, or water vapor. If Tau Ceti is too hot for surface life, it could still harbor life in subsurface environments. On Earth, extremophiles thrive in deep underground aquifers and hydrothermal systems where sunlight is absent, but chemical and geothermal energy are abundant. If Tau Ceti possesses internal heat sources and retains subsurface water, similar conditions could exist beneath the surface, shielded from any harsh surface climate. In conclusion, Tau Ceti remains one of the more intriguing nearby super-Earths due to its Earth-like host star, relatively stable environment, and mass suggestive of a rocky composition. However, its position close to the inner edge of the habitable zone raises the possibility of high surface temperatures and a potential greenhouse climate. The planet's actual habitability depends on atmospheric and geological factors we cannot yet measure. It may be a scorched, arid world like Venus, or under the right circumstances, a planet with clouds, oceans, and the capacity to support life. Whether life exists there is unknown, but Tau Ceti stands as a compelling target in the broader search for life beyond Earth. Gliese 667 cc lies nestled in the arms of a distant trinary star system, three suns bound together in a cosmic dance, drifting through the constellation of Scorpius, just over 23 light-years from Earth. This exoplanet, a super-Earth with a rocky surface and the right amount of starlight, circles a small red dwarf known as Gliese 667c. And tonight, as your mind winds down, we set sail in imagination to this serene and silent world. Gliese 667cc was first confirmed in 2011, thanks to the painstaking efforts of astronomers using the European Southern Observatory's HARPS instrument in Chile. Instead of watching for the planet's silhouette as it passed in front of its star, they listened, watching for tiny shifts in the star's motion. When a planet orbits a star, it pulls slightly on it, tugging it gently back and forth. This wobble in the star's light revealed something remarkable: a rocky world about 4.5 times the mass of Earth, orbiting in the heart of the star's habitable zone. Now let yourself drift through space, past the dusty edges of our solar system, through interstellar night, to arrive at Gliese 667cc. If you could stand on its surface, On a plane of stone and shadow, you would feel a gravity stronger than Earth's, though not overwhelming. It might be enough to ground you firmly, to keep your steps measured and strong. The world is likely tidally locked, with one face always turned toward its star and the other in endless darkness. But along the delicate twilight line, where day becomes night, temperatures could be mild, not too hot, not too cold. A twilight realm, glowing softly in the red-orange light of a quiet star. This small red sun, Gliese 667c, is only about a third the mass of our sun and emits far less heat. That means its habitable zone, the distance where water can remain liquid, is much closer in. Gliese 667cc orbits its star every 28 Earth days, hugging close enough to receive just the right amount of energy. And because it's part of a triple star system, there may be moments, if the sky is clear, when two other suns appear as bright stars on the horizon, companions to the central glow. If this planet has an atmosphere, it may circulate warmth around the globe, softening the differences between day and night. Winds could carry clouds from the daylit side to the night side, forming rains, rivers, and perhaps even oceans. Water, the lifeblood of biology, may move in endless cycles beneath the dim red light. Imagine the sky, a soft, reddish glow that never quite reaches the brightness of daylight on Earth. Imagine dark leaf plants stretching toward that gentle warmth, photosynthesizing not with green chlorophyll but with pigments evolved to harness red and infrared light. Forests of shadowy ferns, fields of slow-growing moss. The air might be heavy with moisture or thin and crisp like a mountain dawn. We don't yet know what the atmosphere contains, if it's rich in nitrogen or carbon dioxide or something more exotic. But the planet's mass suggests it is rocky, with enough gravity to hold a protective envelope of gases. If so, that atmosphere could shield the surface from radiation, allowing complex chemistry to evolve. Some models even suggest that Gliese 667cc may be more suitable for life than Earth, its stable climate, gentle sunlight, and long lifespan providing the perfect incubator for biology. Its star, Gliese 667c, is much older than our sun. It burns cooler and more steadily and will live for hundreds of billions of years. This cosmic longevity means that if life ever took root there, it may have had far more time to evolve, adapt, and flourish than it has had here. What might such life look like? Perhaps nothing like us. Perhaps simpler, microbes clinging to the undersides of rocks, or single-celled organisms floating in darkened seas. Or perhaps, given the right conditions, life there has grown complex. Swimmers beneath alien waves, flyers gliding through reddish mists, crawlers, thinkers, watchers. Or perhaps the planet is quiet, barren but beautiful, with only wind and stone and starlight. Still, it beckons. Gliese 667cc is not an isolated dream. It is one of several planets orbiting Gliese 667c and part of a system that has become a favorite of planetary scientists. The trinary nature of the larger system adds to its mystery and appeal. 3 stars sharing space, with planets tucked among them, weaving their own small rhythms in a grander celestial symphony. It is easy to imagine a civilization rising there, watching not 1 but 3 stars traverse the sky, calculating the passage of time by their conjunctions, their brightness, their fading. Or perhaps there are no civilizations, only oceans, only cloud-wrapped continents, only silence and potential. Even now, Earth-based telescopes and space observatories continue to listen, to watch, to analyze the spectral fingerprints of planets like Gliese 667cc. Future missions may let us probe its skies more deeply, revealing whether it holds the traces of water vapor, oxygen, methane, gases that could hint at something alive. But until then, it remains a possibility, a hope glimmering just beyond the veil of night. So now, let yourself breathe deeply. Let your thoughts drift outward, past Earth, past the moon, past the reach of sunlight and into the soft, dark cold of space. Let yourself float toward that quiet system in Scorpio, toward a rocky planet under a red sun. You are safe. You are weightless. You are carried by the imagination of humankind, the same imagination that led us to find Gliese 667 cc in the first place. HD 40307G is a potentially rocky exoplanet orbiting the K-type main sequence star HD 40307, located approximately 42 light-years from Earth in the constellation Pictor. Discovered in 2012 through the radial velocity method using the HARP spectrograph at the La Silla Observatory, HD 40307G quickly gained attention as one of the more promising candidates for habitability. It is the outermost known planet in a system that contains at least 6 planets, and it orbits its star at a distance that places it comfortably within the star's habitable zone. HD 40307G has a minimum mass of approximately 7.1 Earth masses, classifying it as a super-Earth. Although its radius is unknown due to the lack of observed transits, models suggest it is likely a rocky or water-rich planet with a surface gravity significantly stronger than Earth's, possibly up to 2G, depending on its true composition and internal structure. This increased gravity would improve its ability to retain a dense atmosphere, which is crucial for long-term climate stability and the potential for surface liquid water. The host star, HD 40307, is a K2.5 V-type star with about 75% the mass of the Sun and less than half of its luminosity. As a cooler and less luminous star, its habitable zone lies closer in than the Sun's. HD 40307G orbits at approximately 0.6 AU with an orbital period of about 198 days, receiving about 62% of the stellar flux that Earth receives. This energy input places it firmly within the conservative habitable zone, where surface temperatures could, under the right atmospheric conditions, support the presence of liquid water. Because HD 40307G was discovered via radial velocity and does not transit its star, no direct measurements of its atmospheric composition, surface temperature, or albedo are currently available. As such, its climate and habitability must be inferred through modeling. These models suggest that if the planet has an atmosphere with greenhouse gases like carbon dioxide and water vapor, it could warm sufficiently to support Earth-like surface conditions. A dense atmosphere would also help redistribute heat across the surface, especially if the planet is tidally locked, a possibility given its proximity to its star. Tidally locked planets have one hemisphere permanently facing their star and the other in perpetual darkness. However, HD 40307G's relatively long orbital period and its distance from the star reduce the likelihood of a 1-1 spin orbit resonance. It may instead be in a higher order resonance, such as 3-2 like Mercury, allowing it to experience both day and night. If this is the case, the planet could enjoy a more Earth-like climate dynamic, improving the chances for habitability. The strength and stability of HD 40307G's atmosphere are crucial. A thick Earth-like or Venus-like atmosphere could shield the surface from cosmic and stellar radiation, regulate temperatures, and support complex weather systems. The planet's higher mass means it may have retained its primordial atmosphere more effectively than Earth. It also increases the likelihood of internal heating, potentially driving geological activity such as volcanism, which would replenish atmospheric gases over time and help support a carbon silicate weathering cycle that stabilizes climate. HD 40307 itself is a relatively quiet, old, and stable star with low stellar activity. It does not show the intense flaring behavior that many M dwarfs and even some younger K dwarfs exhibit. This low activity environment is ideal for atmospheric retention and biological stability. A calm stellar environment reduces the risk of harmful radiation stripping the atmosphere or disrupting potential biological processes on the surface. One intriguing possibility is that HD 40307G is a water world. If it formed farther out in the protoplanetary disk and migrated inward, it could have retained a significant amount of water, ice, and volatiles. In such a scenario, the planet may be covered by a deep global ocean with no exposed land masses. A water world could support life in the upper layers of the ocean, where light penetration and nutrient mixing could drive photosynthesis and basic biological cycles. Alternatively, life could exist around hydrothermal vents at the seafloor, where chemical energy powers microbial ecosystems similar to those found on Earth. However, life on a water world would face limitations. Without land, certain geochemical cycles may be suppressed, and nutrients like phosphorus may be less available. The absence of a rocky surface could also limit tectonic activity, reducing the long-term recycling of carbon and other essential elements. Still, ocean planets are not inherently less habitable. They simply represent a different kind of biosphere, one that could be rich in microbial or even complex aquatic life, depending on evolutionary pressures and environmental stability. In contrast, if HD 40307G is a rocky planet with significant land area, it could feature a wide range of habitats, from oceans and lakes to deserts and highlands, depending on its atmospheric dynamics and axial tilt. Its climate might be dominated by strong weather systems due to the higher gravity and possibly thicker atmosphere, but the presence of land would allow the planet to support silicate weathering, which stabilizes atmospheric carbon dioxide levels and contributes to long-term climate regulation. The potential for a magnetic field is also worth considering. If HD 40307G has a multimetallic core, it could generate a magnetic field through dynamo action, just like Earth. This field would protect the atmosphere from erosion by stellar wind and cosmic rays and could help preserve surface habitability over billions of years. The high mass of the planet increases the likelihood of ongoing internal heat, supporting the maintenance of a liquid core and tectonic processes. From an astrobiological standpoint, HD 40307G is a compelling target. All three essential ingredients for life as we know it, liquid water, an energy source, and bioessential elements, are plausibly present. The energy could come from sunlight if the atmosphere is transparent and the surface is illuminated, or from geothermal sources if the planet has significant internal heat. The elements required for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are expected to be common in planets formed around stars like HD 40307, especially if the planet accreted material from both icy and rocky regions during formation. At present, there is no observational evidence of life or even atmospheric characteristics for HD 40307G. Its discovery via radial velocity means it does not transit and thus cannot be studied through transmission spectroscopy with current telescopes. Future missions designed for direct imaging, such as the proposed LUV, O, IR, or HABEX telescopes, could eventually characterize its atmosphere and search for biosignatures like oxygen, methane, or ozone. High-contrast imaging and reflected light spectroscopy may also reveal cloud patterns, atmospheric composition, and surface conditions. In summary, HD 40307G is one of the most promising known super-Earths for potential habitability. It orbits a stable low-activity star within the habitable zone, likely has a rocky or ocean-rich composition, and is massive enough to retain a thick atmosphere. Whether it is a Venus-like greenhouse world, a temperate rocky Earth analog, or a vast water-covered planet, remains unknown, but its characteristics place it high on the list of targets in the search for alien life. Until we can directly observe its atmosphere, the question of whether HD 40307G harbors life will remain one of the most compelling scientific mysteries. Many of these planets orbit red dwarfs, the most common type of star in the galaxy. These stars offer long lifespans but also produce high levels of stellar activity, particularly in their youth. Despite the risk of atmospheric stripping and flaring, several planets around such stars may still retain atmospheres, depending on their magnetic fields and initial conditions. Planets like those in the TRAPPIST1 system or orbiting stars like Ross 128 show that even in harsh environments, there may be protective mechanisms or zones, such as twilight regions on tidally locked worlds, where habitability could persist. A recurring theme is the diversity of planetary conditions that might support life. Some candidates appear to be rocky and Earth-sized, others are more massive super-Earths with stronger gravity and the potential to hold onto thick atmospheres. Some, like K218b and Kepler-62e, may be water worlds entirely covered by oceans. These oceanic environments, while lacking land masses and traditional geochemical cycles, could support life in layers of water warmed by geothermal heat or sustained by chemical gradients in deep ocean vents. Others might be rocky with potential for continents, plate tectonics, and weather cycles, all conducive to more complex and stable biospheres. Even among those in the habitable zone, the presence of liquid water is never a given. Temperature alone is not sufficient. Atmospheric pressure, composition, greenhouse effects, magnetic fields, and internal heat all shape a planet's true environment. Planets with higher masses, such as LHS 1140b or HD 40307g, are more likely to retain thick atmospheres and possibly internal heat, improving their chances for long-term surface liquid water. Some planets may have been habitable in the past, but are now transitioning out of it, like Kepler 452b, hinting at how dynamic planetary climates can be. For every factor that works against habitability, stellar flares, tidal locking, thick clouds of hydrogen and helium, there are others that balance the scales. Atmospheric modeling has shown that even tidally locked planets can sustain temperate climates if their atmospheres are thick enough to redistribute heat. Even planets close to volatile stars may have developed atmospheric compositions resilient to stripping. The wide range of planetary configurations we've discovered suggests that life might not be limited to Earth-like conditions. It may emerge and adapt under very different skies. Although we have yet to confirm life on any of these worlds, technological progress is rapidly closing the gap between speculation and evidence. Space telescopes such as James Webb are beginning to examine exoplanetary atmospheres in unprecedented detail, looking for biosignatures, gases like oxygen, methane, and ozone that, when found in the right ratios, could point to biological processes. Transmission spectroscopy, direct imaging, and reflected light analysis will soon allow us to glimpse surfaces, clouds, and perhaps even seasonal changes on exoplanets. Our understanding of life is also broadening. We now know that microbes on Earth survive in acidic lakes, deep sea vents, and frozen tundra. Extremophiles push the boundaries of what biology can endure, hinting that alien life might be thriving in conditions we once deemed inhospitable. Planets once written off as too cold, too hot, or too irradiated are being reconsidered in light of this adaptability. The fact that so many potentially habitable planets have been found within just a few dozen light years is telling. If habitability is this common in our cosmic neighborhood, it may be widespread across the entire Milky Way. Conservative estimates suggest that billions of Earth-sized planets orbit in the habitable zones of their stars. If life emerges easily given the right ingredients, water, energy, and organic chemistry, then it's no longer a matter of if, but where and how often. What form this life might take is unknown. It could be microbial, thriving quietly in oceans or below the surface. It might be more complex, shaped by alien chemistries and evolutionary paths unfamiliar to us. It could even be intelligent, peering out into space just as we are, wondering if it too is alone. But even without encountering intelligence, the discovery of life, any life, beyond Earth would be one of the most profound moments in human history. The search continues, patient and methodical. Each planet studied brings us closer to an answer. Even negative results, the absence of certain gases, barren rocky surfaces, or lifeless oceans, teach us what is required for life to take hold. And in the process, they sharpen our understanding of our own world, our own atmosphere, and the delicate balance that sustains us. We are, in a very real sense, standing on the edge of discovery. The worlds we've examined do not offer certainty, but they do offer hope. Hope that life is not a singular miracle, but a natural outcome of the universe's chemistry and order. Hope that the spark of biology flickers not only here, but everywhere it is given a chance. So we look up. We build telescopes. We run simulations. And we listen, not just for alien signals, but for the subtle, quiet signs of life breathing in the dark. These exoplanets, some warm and watery, others strange and dim, remind us that our universe is not silent, it is full of questions. And among them, the most enduring, are we alone? The answer may come not with a roar, but with a whisper from the wind on an alien sea or the chemistry of a distant sky. Until then, we remain watchers of the stars, seekers of the unseen, and dreamers on a pale blue dot, hoping that somewhere out there, life has taken hold and is waiting to be found.